Our next couple of examples deal with determining what the domain and range is of a function. Recall that the domain is the set of x values in the function, and the range is the set of y values of your function. So on example 8, it says to determine the domain and range for the function shown. These are all functions. They pass the vertical line test. Now we can discuss the domain and the range. The domain is the set of all x values. So we have an x value of -4, of -2, of 0, of 2, and of 4. All right? That would be the set of all the x values. And the range is the set of all y values. Let's see, we've got a y value at -2, another y value at 0, at 2, 4, and 6. So the range is the set of -2, 0, 2, 4, and 6. On number 90, the domain is the set of all x values, and so we have action occurring for our x values all the way from really large negative values all the way up to 4, not including 4. And so how we would write the domain would be all values of x from -infinity up to 4, with a parenthesis by 4, not including the 4. Another way that you could write this is you could say the domain consists of all values of x such that x values are less than 4. That's a way to write your domain in set builder notation. For our range, okay, you see the arrow that points down saying that these values will keep on going down. So we're going to have values that are from negative large numbers. So again, -infinity all the way up to and including 4. Okay? So that would be a bracket if you want to look at your number line that way. So your range would be from -infinity up to and including that y value of 4. So notice the bracket. Or you could say the range is the set of all our function values. I don't know if this thing was called f of x or k of x or what it was. So I'm just going to say the set of all y values such that y is less than or equal to 4. On number 94, what the arrows on the end of that parabola keep on pointing down say that for our domain, we're going to have x values taken care of all across our domain. So on our domain, it's everything from -infinity up to +infinity. Or you could just say all real numbers, something along those lines. Okay? Now, for our range, we look at the set of all y values, and that is again going to be y values happen when we've got negative large numbers all the way up to and including 2. So the range would be from -infinity up to and including 2. Or again, we can say the range is the set of all y values such that y is less than or equal to 2. Okay? Now, on our next set of examples, we're going to need to look at the guidelines just given an equation and not a graph. How do we determine what the domain would be? Well, we do have two things that we need to consider. It says to determine the domain of a function defined by y equals f of x. It says to exclude all the values of x from our domain that make the denominator of a fraction 0. Okay, that should be nothing new. And since we're talking about real numbers that would lie in our rectangular coordinate plane, we must also exclude values from our domain that make the radicand negative within an even indexed root. So what that's saying is no negatives under a square root, no negatives under a fourth root, no negatives under a sixth root. We're going to exclude values that would make that happen, right? So on example 9, it says write the domain in interval notation. They don't say domain and range because the range is a little bit more difficult to find. We'll be exploring a way to do that a little bit later on in chapter 2. But for right now, on number 98, okay, we want to make sure that the denominator can't be equal to 0. So we want x minus 2 to not be equal to 0. And if you think about adding 2 to both sides, you know that if x is equal to 2, that's going to make that denominator be 0. So the domain of the k of x function is everything but 2. You might say the set of all x values such that x is not equal to 2. Or if you want to state that in, actually we better do that in interval notation because that's what our directions asked for. What you're thinking about is for your domain, it's going to be all the values on your number line except for 2. And so that would consist of everything from negative infinity up to 2, unioned with everything from positive 2 to infinity. And this is really what we were wanting in interval notation, and that means our whole number line, everything from negative infinity to positive infinity, but not 2. We know it doesn't include 2 because of the parenthesis there by the 2. Okay? On part B on this example, we want to make sure that x squared plus 2 is not going to be equal to 0. Now, if you just think about this, there is no way that x squared plus 2 will be equal to 0 because no matter what x is, when you square that, you get 0 or a positive. And then when you take 0 or a positive number and add 2 to that, you're not going to get 0. All right? So that's not going to happen. Okay? We have no problem areas. X can be all reals. So we would say for the domain, the whole shebang, our whole entire number line, everything from negative infinity to positive infinity. There's our domain expressed in interval notation. Now, the example on number 100, we're going to look at those radical parts. Okay? Remember, we don't want, since we have a square root here, we do not want that quantity of 16 minus t taking on a negative value. What we want, and on problems like this, take your radicand, that's the 16 minus t, and say, all right, we're going to be okay. We're going to have values for t in our domain as long as that radicand quantity stays greater than or equal to 0. That means 0 or positive. We can always take the square root of 0 or a square root of a positive number, and that's what that greater than or equal to 0 guarantees. Now, if we solve this for t by, this was a pretty easy one to solve for t, add t to, add t to both sides. I don't know where that 6 came from, but there we go. Add t to both sides. We have 16 is greater than or equal to t, and that can also be written as t is less than or equal to 16. Okay? So we're talking about values of t that are less than or equal to 16. If you want to graph that interval on a number line, then from that it's easier to see what our domain in interval notation will be. It's going to go from negative infinity, comma, up to and including 16. Okay? There's our domain in interval notation. All right, let's look at part B now. On this one, we're going to again take the radical, the t minus 16 and say you better stay greater than or equal to 0. As long as t minus 16 stays greater than or equal to 0, u values of t can be in our domain. To solve this for t, add 16 to both sides. And this will state t needs to be greater than or equal to 0 plus 16 is 16. Okay? These values of t need to be bigger than or equal to 16. So the domain of this function is 16 to infinity. Those are the values of t that will make sure that we don't get a negative underneath that square root. For example, okay, what would be w at, 18? Okay, that's bigger than, that's greater than or equal to 16. Can we say that this is going to be a real number? Yeah, that is just square root of 2. That's real, okay? So that 18 is in our domain, and any value of t that is greater than or equal to 16 will be in our domain. Let's look at number 106. On this one, with the absolute value, did they say anything here in the guidelines in the purple box about absolute values? No, for all values of a, we're going to get a real number, okay? So there's no restrictions here. There's no restrictions for a in our domain. The domain of this one is going to be the set of all real numbers expressed in interval notation. That's everything from negative infinity to positive infinity. Now, when that quantity is put in the denominator, like on example B, we need to make sure that this denominator doesn't take on a value of 0. Okay? If that happens, those numbers are not in our domain. So I'm going to take the 8 minus the absolute value of a minus 2, and I'm going to say you can't be equal to 0, because any values that satisfy that would not be in our domain for a. All right, to solve these absolute value inequalities, I'm going to isolate the absolute value first. That was always our first step. So I'm going to have 8 can't be equal to the absolute value of a minus 2. And do you recall how to handle an absolute value equation? We break that apart into two different equations. One of them we say a minus 2 can't be equal to 8. And we say a minus 2 can't be equal to a negative 8. Now, if we add 2 to both sides over here, we say a can't be equal to 10. Y'all think about that. If a is equal to 10 here, we're going to have 5 over, all that will come out to be 0. And 5 over 0 is not a real number. Okay, back over here on this other one, again, add 2 to both sides. Okay, when we add 2 to the negative 8, we get negative 6. So our domain, the values that can't be in our domain are 10 and negative 6. Now, the way to write that domain is to write, well, the a values can be anything else but 10 and negative 6. So we're going to say, and if you think about drawing that on your number line, and it can't be negative 6 and it can't be 10, but it can be anything else, that might help us decide how we're going to write our domain in interval notation. It's going to be everything from negative infinity up to negative 6, but not equal to negative 6, union with stuff in between negative 6 and 10, so that's stuff from negative 6 to positive 10, and then we could also have values of a in our domain that are greater than 10. So that is parenthesis 10 to positive infinity. And that is our domain written in interval notation.